Hello, and welcome to my talk, Inferring User Height and Improving Impersonation Attacks in Mobile Payments Using a Smartwatch. I'm Jack Sturgis, a DPhil student at the University of Oxford, and this project was completed jointly with Simon Ebers, Ivo Sluganovic, and Ivan Martinovic. The popularity of cashless payment systems has grown rapidly in recent years. In the UK, card payments surpassed cash for the first time in 2018. NFC-enabled tap and pay systems, primarily used on smartphones, account for approximately a quarter of overall market share, according to market research conducted by Technavio. In recent years, these systems have been implemented on smartwatches, enabling the user to make offline mobile payments over NFC using a smartwatch even when no smartphone is present. However, smartwatches have much smaller screens than smartphones, making the entry of a PIN tedious. And unlike smartphones, current smartwatches lack fingerprint readers and facial cameras that would enable the convenient biometric authentication options that most smartphone users enjoy. This presents an opportunity for implicit authentication in the form of behavioral biometrics. In 2016, work by Shrestha et al. Showed that the tap gestures made by the user when making a payment with a smartphone, as measured by various inertial, position, and environmental sensors on the smartphone, could be used as a behavioral biometric to authenticate the user implicitly as part of the payment procedure. In 2017, work by Lee et al. Showed that a user could similarly be authenticated on a smartphone as they picked it up, this time using only the phone's inertial sensors. So in our previous work, we investigated whether we could achieve similar results with a smartwatch, and we showed that we can authenticate the user using only tap gestures during a mobile payment. Building on that work, we move our focus to how wrist motion data might violate user privacy and how an adversary might make use of such insights. In 2015, work by Riaz et al. Showed that inertial sensor data taken from 4 sensors worn on a user's ankle, wrist, back, and chest were, quite accurately, able to infer the user's age, sex, and height. The authors did, however, note that the wrist data contributed the least to those inferences. So we decided to investigate the correlation between users' age, sex, or height and their tap gestures. If we can infer any such information from the tap gesture data, then we'll consider there to be a connection. And moreover, we'll assume that an informed attacker can capitalize on that connection by selecting a victim of similar age, sex, or height, whose tap gestures will be inherently similar. We consider a system model in which the user is wearing a smartwatch and standing in front of a platform. The platform has on it 6 fixed point-of-sale terminals and a 7th unfixed or freestyle terminal that the user picks up from the center of the platform. The user performs tap gestures on the terminals, which collect timestamps when an NFC connection is established, and a background app on the smartwatch that collects the inertial sensor data. That data is later segmented into tap gestures using the timestamps. We collected our data using a Samsung Galaxy Watch running the Tizen 4 operating system. This watch has an accelerometer and a gyroscope, and also offers derived values for linear acceleration and approximate orientation. The image shows the sensor axes when the watch is worn on the user's left wrist, where the positive x-axis points towards the hand and the positive z-axis projects out through the watch face. We conducted a small user study of 16 participants, the demographics of whom are shown here. Each participant attended 3 sessions and in total performed 30 tap gestures on each terminal, or 210 gestures overall. From each NFC contact point timestamp, shown in red on this slide, we retrieve a tap gesture as expressed by our 4 inertial sensors. In this exemplar gesture, we infer from the accelerometer data that the watch reached the terminal 1.5 seconds before the NFC contact point, and then from the gyroscope and orientation data, that the user adjusted the orientation of the watch face against the terminal to find the NFC signal. We retrieved each gesture sample in different window sizes, and by sliding those windows by different offsets from the NFC contact point, in order to find optimal gesture parameters. We then extracted 220 features from each sample in each window and trained random forest classifiers for each of our models. For our age and sex inferring models, we trained multi and binary class classifiers, respectively, in a leave one out manner. That is, for each user, we trained the classifier on the tap gestures of other users. For these models, we found no correlation with our tap gesture data. That is, we were not able to infer age or sex accurately from tap gesture data. Our sex inferring model achieved significantly better results than our age inferring model, perhaps because sex correlates well with height. However, our data set contained both male and female outliers with respect to height, and so this expected correlation may not have reified. For our height inferring model, we trained regressors over height values between 158 and 194 centimeters, rounded to the nearest half centimeter. This model performed much better. We show the R-squared scores for our height inferring model in this heat map. Each window in the heat map represents the same set of gestures, but processed in different window sizes and time offsets from the NFC contact point. Those windows above the red line represent gestures performed entirely before the NFC contact point. This is not especially relevant here, but it will be relevant when we discuss authentication, since these will be the potential gestures available at the time of payment by which an authentication decision will be informed. We see in this heat map that the best scores are achieved with gestures that end a few seconds after the NFC contact point and have a window size sufficiently large as to have initiated before it. In other words, the most effective discriminator between users of different heights is not in reaching towards the terminal, but the subsequent withdrawal from it. We observe that when users pulled away from the terminal, they unconsciously erected their back and withdrew their arm at an angle roughly proportional to their height, thus betraying their height. This is in contrast to the reaching movements towards the terminal that were more deliberate, anticipatory, and constrained by the position of the terminal. We also trained a second height inferring model using tap gestures obtained from a single terminal. We see in the second heat map that these results are better still, especially in the regions where the first model did well. This suggests that for repeated use of the same terminal, or for use of standardized terminals such as those on public transport systems, height inference is particularly effective. Now that we have seen a correlation between tap gestures and height, we can test the hypothesis to see if an informed attacker can gain an advantage over a naive attacker by selecting victims by height. We consider a threat model in which the adversary has stolen a legitimate user's smartwatch, has unlocked it, is wearing it, and is attempting to make a payment with it. We have a naive or zero-effort attacker that selects victims at random, and an informed attacker that selects victims that are similar in height to within 1 centimeter. We aim to show that the informed attacker is more successful. We create an authentication model that uses a different classifier for each victim-attacker pairing. Since this is an authentication use case, we ensure that each training set contains the victim's gestures from only the first 2 data collection sessions, and that the gestures from the 3rd session are used for verification. This is analogous to the enrollment phase preceding an authentication phase in practice. We include other users' gestures in the training set as the negative class, but none of the attackers. For in-store authentication, we focus only on windows with an offset of greater than or equal to 0, so that the tap gesture is completed at or before the NFC contact point, which is when the authentication decision is made. For the naive attacker, we average each window over every pairing. For the informed attacker, we average each window only over those pairings where the height difference is less than or equal to 1 centimeter. We use the equal error rate as our performance metric and compare the two. The results in this heat map show how much greater the equal error rate and therefore the false acceptance rate of the informed attacker is compared to the naive attacker in each window. It is worth noting that in our previous work, we found the optimum gesture parameters for in-store authentication to be a window size of 2.5 seconds with an offset of 0. On this heat map, we see that an informed attacker can passively increase the false acceptance rate of that window by 14.9%, thereby increasing the chance of a successful impersonation attempt. This plot shows each victim-attacker pair arranged by their difference in height, and the results for each victim are shown with a consistent color throughout. With the exception of 3 victims, shown with hatching or dot textures, the average equal error rates decrease steadily as the difference in height increases. We note that the tallest user in the dataset, shown in light green with dots, almost always yields a significantly greater equal error rate than when he is the attacker in the same pairing. This suggests that he is particularly susceptible to impersonation. In this work, we showed that a user's height can be inferred from tap gestures, and that an informed attacker can increase the chance of a successful impersonation attempt by selecting a victim of a similar height. The primary limitation of this work is its small data set. Unfortunately, our experimental work was cut short by lockdowns. Future work will look to increase the size of the data set and to investigate the counter trend presented by the tallest user. We would also like to investigate the feasibility of using height inference from historic tap gesture data, were it to be collected, in retroactive fraud analysis to identify impersonators. And with that, I conclude the talk. Thank you for your attention.